Okay everybody, today's video is going to be on the audio signal flow that we see from a mobile going through our microwave system over to dispatch, and we're going to track it all the way through and see all the different transformations it makes on its way from getting a voice from here in Santa Rosa over to a dispatcher here in Prairie City. Now, we would normally not need any of this stuff if these people could hear each other, but once they get apart a certain distance, they rely on this equipment to further extend their ability to talk to one another. And there is an initial distance that you can get using two-way radios. But when that is even too short a distance, you have to use a way to do an extended connection, and that's what we use our microwave system for, is to connect people who are hundreds of miles separated from each other, where their local two-way radio or repeater would not be able to cover the distance that they need to cover. So we're gonna have a look at this, and like I said, we're not going to go into too much detail because some of the stuff is very complicated, but we are going to follow it all the way through without having any black boxes of magic happens here. So hopefully when we're all done, it'll make a lot more sense and be a lot clearer. We're going to take little sections at a time here to go through, and then when we're all done, we'll do a big picture wrap up again. So I want to start off with coming over to this section right here, this initial section where we begin with an officer out in the field, and he needs to talk to dispatch. So he's going to use his two-way radio here and make a connection from his radio to the closest mountaintop repeater, which in this case is going to be Mount St. Helena, and this is how he's initially going to get into the system and get on his way over to Prairie City. So let's start with this little branch first, and then we'll head to the next section. So if we move over here, this is a blow up of our first section. We have our two-way radio here, and we have our repeater receiver here, and it's pretty straightforward. Everybody understands. You talk into the microphone here, goes out the antenna and comes into the other antenna, and the sound comes out. Some of the things I want to go over real fast is this idea of signal and transferring signal and signal flow, or what's more accurate and what you should try and have in mind is that we don't actually transfer the signal itself. What we do is we take multiple snapshots, pictures of this sound, of the information in the sound, and we reproduce it at different spots along the journey. And the reproductions are never the same as the original signal. But the only thing that we have to accomplish is to be able to fake out the human ear. As long as the person on the other side thinks that the sound is good enough and there's nothing that's alerting them to some kind of quality or something about the sound that's not right, that's all we need to accomplish. We're not trying to get exact anything. So keep that in mind, that we're going to go through several things of, well, this is where the original signal ends, or where this is where this signal ends, and this is where we take a picture of it and then reproduce it on the other side. So we're going to start right here with the original audio coming in, and this would be the voice of the mobile user, and this would be vibrating air vibrations coming in that's hitting this microphone right here. Now, this microphone has a little crystal inside it called a piezoelectric crystal, and it has a unique ability of taking mechanical vibrations and translating them into equivalent electrical signals. This microphone does a fair job at reproducing the sound, but once again, it's not exact. And there's a whole industry around these microphones. You can buy thousand microphones that cost thousands of dollars simply because they have the ability to more accurately reproduce the original sound. So this would be for music or broadcast purposes. But once again, every electronic device that we have come along the thing will not be 100% accurate. So the vibrating air comes into the microphone here, electrical signal comes out, audio electricity, it's amplified, and then it's used to frequency modulate an RF carrier. And what the transmitter does is it produces a continuous amount of power, and the only thing that changes on the transmitter is that the frequency goes up and down in relationship to, in synchronicity with the audio coming in. It's not a 100% accurate representation of what's coming in. Once again, if you did super careful measurements, you would see discrepancies and distortions that weren't there in the original package. But the big thing to understand is that we are not putting this signal on this carrier. We're simply mimicking the signal by moving the carrier up and down in frequency, but the signal itself is not here. So, and that's going to be real important to understand. It's a big concept when we get to our next phase, which is the receiver. So when this electricity that comes out the coaxial cable gets here to the antenna and starts going up and down the radiating element, causing the electron orbits to in the atoms to jump up and collapse back down, which is the mechanism of releasing the RF photons that come out, the radiated energy. When that signal comes off the antenna and goes across through the air and clips into this receiving antenna here, it induces electricity with the moving of electrons back that goes through this coaxial cable back into the receiver. Now, this electrical signal coming down here is simply a signal that just so happens to be changing frequency in relationship to the original audio coming in, but it's not the audio. It's an RF carrier. And what we do is we do a little trick where we inject a steady signal into that varying RF signal coming in, and we produce what's called an IF, an intermediate frequency, that we then do again. We mix again in a process called super heterodyne, and that's how we eventually get we recover our audio out. But the audio that comes out is a reproduction of the original audio going in. It is not the actual audio. So any of the parts and pieces of the transmitter assembly or the receiver assembly here that's out of spec or not right or not perfect, every one of them contributes to the fact that this reproduction is slightly different than what came in. It's got stuff on it now that the original one did not have. But once again, our human ears aren't that picky, and we can't perceive those kind of minute changes. And as long as our equipment is in reasonably good tune and we're in reasonably good distance, it works perfectly fine for our purposes. So through this initial process, once again, it translates into virtual wires, so that the sound coming in off this microphone is able to traverse this distance in space and come out the radio essentially the same way it looked coming out of the microphone. So we're just going to go ahead and work with that and use that as our reference. So we have the back to where we're at. We have sound coming in and we have sound coming out, and we're ready to move on to the next step. So on the next part of the route, what we're doing is we're taking that sound and we need to take it from Mount St. Helena and we need to take it all the way to Prairie City. And the path that we get to Prairie City is from Mount St. Helena to Vaca, to Burkett Tower, to Pine Hill, and then to Prairie City. So let's take these one at a time and follow along how it does it. Okay, the analog audio coming in to the T1 channel bank will need to be digitized and digitally sampled to continue the journey across. And so let's take a look at what's going on when we digitally sample an analog signal and essentially convert it into zeros and ones. And then after we convert it to 0 and 1s, we recreate it at the far end to try and get it back to as close as we can to where it came in. So some of the things about the sample that you should know is Nyquist theorem, and it basically is letting us know that for our voice audio that we're trying to pass through this, that we need to sample 8,000 times per second. That's what it comes down to. So let's talk about what happens 8,000 times a second, and we'll go through the process. We're going to start this as if the audio has already begun, so we don't have to start with any of the very first beginning processes, but this is audio's already begun, so we're going to take a snapshot in time and walk in here and look what's going on. So normally when we think of measuring AC voltage with AC, we think of using the AC voltage measurement. But you can also, if you have the ability to freeze time, you can take an audio signal and any moment do a DC voltage from your reference to where the signal is crossing at that instant moment in time. And that's what we're doing here. That's what the T1 is doing, is that every 125 microseconds, it is doing a DC voltage measurement. Now, this DC voltmeter that's built into here is a special one. It's got a limited range to it, and it can only read in 256 steps. Its range goes from all zeros to all ones, and these are 8 bits range. So when it measures the DC voltage, it takes the reading and essentially, and we're gonna do some simplification, some really big simplification going through these, because some of these things are incredibly complex as far as how they work at the minute level and as far as the system is concerned and all that. And we don't need to worry ourselves with those kind of details because they're irrelevant. We got to remember, at the end of the day, the only thing this entire section of incredibly complex electronics is doing is just simulating 4 wires. At the end of the day, we can always keep it simple because that simply is what it's doing. So back to our sampling situation here. We have the thing, we got our voltmeter, we're getting a measurement every 125 microseconds. When we get that measurement, what's going on is it's recording that measurement, and what it needs to do is it needs to send that measurement to its partner at the other end, where that partner will then take that measurement that it measured and recreate the signal by using a DC power supply that it can adjust to match that exact voltage that it measured in the sample. So the process goes, this guy measures the voltage, writes it down, tells it to this guy reads it, and then sets the voltage out. And they do this 8,000 times a second, where they do a measurement and then they readjust. And if you look at the output of the audio, it's like click, 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 click. They're doing this one step at a time, and because they're doing it so fast, they essentially have the ability to recreate a sine wave. And even though you can see it's got the digital components to it, our ear can't pick that up, and it's for communications purposes for us with the dispatcher and the mobile user. It's not a problem. You cannot detect it. It's not even something that you have to live with. It sounds good. As a matter of fact, all the normal qualities of the voice are there. You could actually recognize the person's voice if it was someone you knew. There's no degradation to the quality for all intents and purposes. So back over to here, where we got this initial measurement and the recording. Now, if these two channel banks had 4 wires, 2 for one direction and 2 for the other, but if they just had 4 wires that connected them together, this information would be sent along those wires directly straight over here to be recreated on this side. But we don't have wires like that because this is hundreds of miles in between here. So we need to have a way of making virtual wires, pseudo wires, and this is what the MPLS Microwave Backhaul system does. It provides essentially an email system so that this information could be written down, placed in an email packet, and sent along the network to pop up at the distant end. And then the information can be opened up and read and then reassembled back to its original form. And this is what we do. We use these values, and we take them and put them in an Ethernet packet in a frame that gets a frame of data, and then we send it along the system through these servers and microwave radios that take it to its destination. Now, we just happen to be using a system called MPLS, and not to get too complicated on MPLS because it is a complicated subject, and there's worlds within worlds with all these things. But the basic thing that you should know is that what makes MPLS a little bit easier to deal with is that when the message is first placed into the envelope, this envelope has in the MPLS system, you have a way to put an address on it that says, in this particular case, in essence it would say Prairie City is where I need to go, and in the normal IP router situation that we normally have. When that envelope reached each destination, that destination would have to open up that envelope, look inside it, read where it was going, put it in a new envelope with a new address, and send it on to the next mountaintop over, where that process would repeat. They would open it up, look on the information inside, see who it was sent to, and move it on through these IP route tables. And that's a little bit burdensome. And with the MPLS system that we have, we essentially only have to put on the initial label, and then as it goes to each successive hop, instead of having to read detailed information about and figure out how it needs to get where it's going, it essentially already has the route and the exit port that it needs to go there already given to it, so that it can do the handoff much more efficiently. And that's kind of it in a short lesson. Like I said, these are all extremely complex things, and they all have their own particular quirks, and all of these things also, I should really mention, they all have ways of error correction, and they get really complex. So it's not worth going into all the exact details about how they work, but just remember this is basically how they work. They're doing a recording, they're sending that information to the other end where they recreate the signal. So let's hop from here, and let's look at a little bit more the last detailed part of the equation, which is how does the MPLS server with its Ethernet output get onto the microwave radio to get transmitted to another mountaintop. And this is where it does truly get kind of in depth, and not for the average person without electronics to get into, because it is complicated. But I think I'm going to just sum it up this way: the MPLS server here, even in its most basic, and you're looking at the very beginning of just one packet of data. This is just like the header and IP information of one packet of data, and all of these zeros and ones basically that come out of the MPLS server, they come out in a streaming fashion, of a serial fashion. We don't have a parallel connection, in other words. So this modulating signal, this input coming in, is extremely fast, and it's not audio like our voice. Like I said, it's a form of data signaling. So these are all zeros and ones, or they'll do 3 or 4 bits at a time to make it more efficient. But bottom line is that we're streaming data into this transmitter here. So unlike the two-way radio transmitter, the microwave transmitter, all we are transmitting is data. It's data right from the very beginning. Now, this transmitter could send out data in the form of just zeros and ones sequentially, and that would be extremely inefficient. But it could just literally send out a stream with zeros and ones. So instead of doing that, the way it can get its speed and its efficiency and the way it does it, it uses a method of modulation called trellis modulation, and it's using another form of modulation called quadrature amplitude modulation, or QAM. And not to get too complicated into it, but you can the way that the QAM works is that you can make a radio signal twist and turn in different ways so that you can have, instead of just a 0 or 1, in this particular configuration, you could have it make 128 distinct individual shapes, if you will, what we call constellations. And this is all in a matter of a dot pattern effect, to where when you adjust the voltage and the phase at a certain way, it makes one of these things pop up at a certain spot and on the receiver, and they can track where it goes. And each one of these spots represents 7 bits of information. So for every one of these spots that you throw up, you're essentially doing 7 bits at once, which greatly increases the amount of data that you can send out at one time in a streaming fashion. But that's what's going on, is that this data is being superimposed on an RF carrier. And just like on the two-way radio, at the other end on the receiver, it is being injected with a steady carrier that allows this original baseband of signal to be recreated at the other end. This signal is not broadcast across the air and then put into receiver. It's broadcast as a representation of it, a copy of it, like a video of a screen, if you will. And as long as the video monitors and the equipment is got enough detail, they are able to recreate the picture at the other end with accuracy. Now, unlike the two-way radio, where there's no error correction at all on the initial part, the microwave radio does have a lot more error correction capability, so that in case any of these bits and pieces go missing, it can request a replacement bit to fill in the spot. And it also has the ability as well that if it loses a gap of time, that it can fill in its own, make a replacement for it, so it's just not blank to get it by. But the reality is that we essentially do perfect reproductions on the digital microwave section. So the thing that comes out the other end of the path, as long as we have good signal strength and no other problems, we can essentially make perfect replications of the signal. That's why when we go back to our big screen, we can go from here and we can go through, not only in this particular case, 3 separate pass-through sites. We could go through 10 different pass-through sites and still maintain perfection the entire way, all the way to the end. And I mean digital perfection, so that every 0 and 1 that goes in on this side comes out exactly the 0 and 1 that went in at the beginning. So that's the more complicated part of it. But the big picture is to remember that once the sound goes out of the mobile, is induced on the carrier here, goes into the receiver, and comes back out, once the sound comes out, the journey between this point and this point, the input to the console, is a straight wire, 2 straight wires in this case, because we're going to use a pair of wires for each side. But that's all this represents. This entire journey right here is just if you had 4 really big really good, really long wires that went all the way from Mount St. Helena to Prairie City. With all the technology that goes in between, all of that technology eventually cancels out so that it, in effect, is hidden. You had it, and its job is done perfectly when it does that. When you have no idea that you actually have traveled through an entire system and popped out the other side. So this is a representation of the one half of the path where the officer is calling in. Now the return journey for the dispatcher's audio that goes back the other direction works the same exact way. There is no difference. It's just another direction, and their audio comes out the repeater going to the mobile. But they are mirror images of each other in the way that they work. And we will eventually have our entire state hooked up in this fashion, except when the final job is done, the radios here will be Ethernet ready, and we will not require the T1 channel banks to be involved at all. So we'll go straight Ethernet from the radio into the server all the way over into an Ethernet ready console, and we will only have a small chunk that's analog. And even then we want to go digital radios between the mobiles and the base. So when that day comes, we will be analog only through the microphone into a small part of the radio. And after that, it will be digital the entire journey until it finally gets to the speaker in the headset of the dispatcher. Okay, and that concludes it, our journey of audio signal flow, and hope that helps you out. Thanks.